Alright, ladies and gentlemen, this is going to be our next video on evolution and specifically looking at evidence for evolution regarding fossils and fossilization. So let's get started on this next video. So what is a fossil? Well, a fossil is the remains or an impression of a prehistoric organism. And it's going to be preserved, it's either going to be petrified or it's going to be cast in this mold in a rock. Now, when we think about fossils, we're thinking about things like dinosaurs. But what I really like to think about fossils as is they're just like a picture. They're kind of like a window into the past. So if we look at this picture here, we can kind of see a combination of the 21st and 20th century blended into this picture. And what pictures really are is they're windows into the past, and they allow you to see what things were like before you were alive or what they were like when you were younger. Now, a fossil is going to be a window into the deep past. We're going to go through and explain how we can go through and look at these windows here. And a fossilization typically requires the burial in the earth. And the way that these fossils are going to form is as time goes by, more sediment is going to pile up. And then as the sediment piles up and creates layers, and then over time as mountains and the sediment erodes away, it exposes these impressions and petrified organisms from prehistoric time. Now, the way we go through and understand how fossils form and the way we discover fossils is via this process called the law of superposition. And it's really a basic law in geochronology, and it's going to state that the youngest layer is at the top and the oldest layer is at the bottom, each layer being younger than the other one beneath it and older than the one above it. So if we were thinking about making a cake, the way you make a cake with icing layers in between is you're going to bake a patty first. You're going to bake this first layer of the cake and you're going to lay that down in the pan. You're then going to go through and put a coating of icing on. And then you'll go through and put another patty down, maybe another coating of icing, another patty, another coating of icing, another patty, and then another coating of icing, and eventually you're going to get to what the toppings are. Well, the oldest layer is at the bottom because that's the one you went through and placed first. And then the subsequent layers as you go through and build the cake continue to pile on top, just like the other cake patties and just like the other layers of icing. So if we're looking at this cake from the side, we can see that the oldest layer was added first, and then all the subsequent younger layers were added later on until we get to the youngest layer, which is at the top, and that's added last. So it's just like going through and assembling a cake. And bakers use this process in order to create ice cream and different layered cakes. And the way I like to think about the law of superposition is basically like going through and making this multi-layered, multi-icing cake. Now, if we look at this diagram here, we can see a representation of the law of superposition. Let's go through and pretend that we are going to be a paleontologist. We're going to dig through these layers here to go through and find fossils here. So let's say in this case we have this dead, let's say it's a dead camel or dead organism here. How did these fossils go through and form? Well, the organism's going to die and they're going to become petrified. Maybe in some cases, like when we find woolly mammoths, we see them encased in ice, but in a lot of times the bone structure is replaced with other minerals and a cast is formed in these rocks and allows these organisms' morphological structure to be preserved. So as a paleontologist, what we're going to go through and do is we're going to travel through each of these layers of the rock. Now, the newest rock is going to be at the top and the oldest rock is going to be at the bottom. And as we go through and travel down each of these layers, we're going to find different layers with different types of fossils. And we can look at how these organisms have evolved over time based on the complexity of these organisms and based on the complexity of the fossils that we go through and find. And as a paleontologist, this is what we're going through and doing. We're looking through these layers of the earth in order to see what the fossils look like and then see how they go through and change over time as we go from older to newer layers. So what I want to look at now is horses and how horses have evolved. And we can go through and look at how horses have evolved based on looking at their ancestors in layers of rock. Now what we see here is at the bottom, the gray is representing the oldest layer of rock, and then we see the most recent layer of rock at the top. Now if we look down in our diagram here, we can see the evolution of the horse. And what we can do is we can use evidence and see how these horses have gone through and evolved based on where we find their ancestors in the layers of the rock here. So in the early Eocene period, we see this Eohippus, and it's only found in this layer of rock. And this is going to date back to 50 million years ago. Then we go into our late Eocene rock and we see this Oligohippus. And as we go through and move up through subsequent layers, we see the Mesohippus, the Merohippus, and then we also see the Pilohippus. And we find each of these individual organisms, their skeletal structures and the fossils of what remain of their skeleton in each of these layers. And then what we can do is we can date the age of the rocks and the rock layers that they're in, and we can go through and look at the fossils and see how this horse has evolved. Now, if we look at the diagram here, right, if we're going up to our modern horse, it's going to be in the most recent rock, but we can look at this diagram here. What we find are these fossils and hoof imprints and molar teeth that allow us to go through and see the changes of the horse over time. So if we go down to our Mesohippus, we see very distinct morphological changes in the forefeet compared to our modern horse. And we can see that as we go up through the different ancestors of that horse, we see some of those, in this case it's going to the bones of 2 and 4, disappear and mold into that one bone. We can also see that the molar teeth are going to get larger and larger, and we can see them both before and after wear, but we can see how those teeth go through and evolve and allow those horse to graze. So over time, we're going through and looking at these fossils in layers of rock to go through and see how these horses have evolved. And we can use this to look at individual species, but then we can also see where speciation events have occurred by looking at the fossils in these different rock layers. So who is going to study fossils? We've already gone through and talked about this in our earlier part, but paleontologists are going to go through and study fossils. Now, Pennsylvania is going to be a great place to actually go through and find fossils. And maybe if your basement is filled with fossils, you can consider yourself kind of an amateur paleontologist. Now, paleontologists are going to work, well, most of them are going to work at universities and museums. And we actually hire, as part of the federal government and as part of the Pennsylvania government, paleontologists to go through and do research and look at the different rock layers there. But paleontologists are going to go through, they're going to look at invertebrates or maybe vertebrate organisms, and they're going to go through and work with geology departments. They can look at how the rock layers have gone through and how different periods of time on the earth have gone through and affected those organisms. And we can also use them to create phylogenetic trees to look at the relatedness of organisms and develop evidence for evolution. But paleontology is an interesting field of study because it allows you to go out into the field and go through and discover potential organisms that we did not know existed. And these are most likely going to be extinct organisms, but it's really interesting to go through and potentially make a discovery of an organism that used to roam the surface of the earth that no longer exists, that nobody else has seen before. And as a paleontologist, you're the first person to really see that organism ever. And we can go through and look at different fossils, and we can see a variety of different things that they're going to go through and show us. So some fossils are going to show how organisms lived, and some fossils are going to show the behavior of organisms that we can go through and deduce from this fossil evidence. They are obviously going to go through and provide evolutionary history to organisms, and that's what we're going through and talking about now. But we can learn a lot of things from fossils. So if we look at an oyster shell, from an oyster shell, just like if we look at the rings on a tree, an oyster shell is also going to have these rings, and each one is going to denote 1 year of its life. So what we can do is we can study oyster fossils, and we can go through and discover how long the oysters lived and in what conditions they lived in. We can also go through and deduce if the climate was favorable to the oysters, and we can see that when the oysters grew more, the rings are going to be larger and thicker. Now, if the oysters went through and struggled for survival, we can deduce from the rings that they are going to be thinner. And thinner rings are going to indicate that the environment is not as favorable. So it was either too warm or too cold, or they were maybe lacking nutrients necessary for them to grow. Now, some fossils are going to show how an organism lived. Amber, for instance, is a hardened fossilized tree resin. And at times the sticky resin drips down from a tree, and it's going to go through and it's going to trap air bubbles and small insects within that resin. Now, paleontologists study amber called fossil resin to observe these complete specimens. Now, the amber can preserve tissue as delicate as dragonflies' wings. We can also see ants that are trapped in amber, and we can see the leaves that they were going through and eating at that period of time. So we can think of these little amber resins as time capsules. Now, we can even go through and look at the air bubbles trapped in the resin, and we can go through and analyze the chemistry of the air. And we can tell whether or not a volcanic eruption has occurred and the atmospheric composition. Now, we can look at the behavior of organisms by going through and looking at fossil evidence. Now, if we go through and look at some of the duck-billed dinosaurs of the time, the hadrosaurs, they lived in large herds. Now, scientists made this hypothesis after observing evidence of social behavior, which included a single site with approximately 10,000 fossilized skeletons. So these fossilized skeletons are going through and providing evidence for us to look at the behavior of the organism. So what these fossils are really providing us with is a time capsule back into the deep past where we can go through and look and observe as to how things were. And from an evolutionary perspective, what it allows us to do is see how organisms have changed over time as we go through and dig into these rock layers. Alright, so did you guys learn? Well, did you learn a couple of things? Did you guys go through and learn about what a fossil is, and then how we go through and discover these fossils via the different rock layers? Did you guys go through and learn about how fossils impact evolution, and do we really understand how superposition goes through and allows us to understand how animals and organisms have evolved over time? And then did you guys go through and learn about what a paleontologist is? This is going to be the end of the video. I will see you all in class tomorrow.